Good morning, everyone. So today we'll be studying density of states in 3D, 2D, 1D, and 0D structures. And for this, first of all, we'll study what their D represents. So D is the dimensionality we are talking about. D here refers to the degrees of freedom in which the electron can go. Okay. So if we are talking about a 3D structure, 3D structure means that in this 3D structure, the electron is free to move in all the three dimensions. So for this, I'm drawing a cube here to represent a 3D structure, because in a cube we can very well represent a three dimensions. So suppose these are the three axes now. If this is your x, this is your y, this is your z. So these are the three dimensions we can easily represent in a cube, and let this is the particle here. So in a 3D structure, the electron is free to move in the x direction, y direction, the z direction. So it has degrees, 3 degrees of freedom in this case. So it is free to, the particle momentum can change in all the three dimensions. Okay, we called such a material as a bulk material. We also called such a material as a bulk material in which the electron is free to go in all the three dimensions. The second thing we will be studying is the 2D structure. So what is a 2D structure? It is two-dimensional structure. It means that electron is only free to go into two dimensions. Okay, the electron cannot go in the third dimension, or we can say in the third dimension it will go, but it can have only some allowed states. So what do we mean by this? So to understand the 2D structure, let us suppress one of the dimension of this cube. So I am suppressing the z dimension. I am reducing the z dimension downwards, and I am suppressing this cube into a sheet now. So 2D structure is now what I am getting. I'm getting some kind of a sheet, because I have suppressed the height of this cube. Now what I have, we have this x-axis, this was the x-axis, we have this y-axis, but we don't have the height because we have suppressed the z-axis. Z was giving the height. So sheet, we can take the example of a plane of paper. So a plain paper do have a width, it do have a length, but it does not have a height. So because y does not have a height, we cannot say that the height is 0, but we can say that the height is negligible. The height of a paper is what? If you go to that, the width, we can say width or height of the paper is negligible. So we can say that electron can go only to some discrete values in the z direction. There are only some certain values that are allowed for electron to go, whereas it can has any width, it can has any length, but height wise it cannot have any height, because the sheet is a very thin material. So such a material we call as a 2D structure, or we can also call such a material as quantum well. We call such a material as quantum well also. Okay, the third thing is one dimension. For the one dimension, what we will be doing now, I will be reducing one more dimension from it. Reducing means I will be quantizing the motion of electron in that direction. Quantize means what? That in that direction now electron cannot take any value, it can only take the quantized value, or we can say it can only take some particular values. So for a 1D structure, now suppose I'm reducing this x directions also. I'm suppressing this sheet like this. If I'm suppressing this x direction also, now what I will get? I will get only a y direction. Means this sheet is now reduced to a wire kind of structure. We have a wire now because आपने x direction को भी reduce कर दिया है. ठीक है, you have reduced the x direction also. So this is what they called such a structure as a quantum wire. In quantum wire, now we can say that the electron can take any length, but it cannot take the width, it cannot take the height. Now you can just imagine a wire you have. The wire can have any length, but the height and width of the wire is very small. If you consider a thin wire, the height and width is very small. Why it is very small? Because the electron can take the values in x and z direction, but there are very certain values it can take. It cannot like take any value and can go to any width. Okay, because you have suppressed those dimension. Now in those dimension it can take only certain values, whereas the dimension which you have not suppressed or not reduced, electron can take any value. Okay, that's why in a one dimensional structure we got a wire, and then it can take any value in the y direction, whereas in x and z direction it can take only certain quantized value. So such a structure we call quantum wire. Next we have 0D structure. Now what do we mean by 0D, zero dimensional structure? Now as the word suggests, zero dimension means there is no degree of freedom in any dimension. It means if I reduce this dimension also, in this case what it was having, it was just having the y dimension. Now if we suppress this y dimension also, if we reduce this also, then what we will get? We will simply get a dot, because now electron cannot go in x, it cannot go in y, it cannot go in z direction. Okay, it's all the three dimensions are reduced, all the three dimensions are quantized. It means in all the three dimensions it can take only certain values. It is like some particle that is encapsulated inside a small box. It does not have any dimension to go around. Okay, so this is a quantum dot. We call it quantum dot. So these are the four kind of structure we are going to study, and in these four kind of structures we are going to study the density of states. So what is the density of state? It is the number of states per unit volume available to the electrons to occupy. Okay, so it is the number of states per unit volume available to the electrons to occupy. So first of all, we will be dealing with the density of states of a 3D structure. So for a 3D structure, there are certain things we have to understand first. So in this 3D structure, the first thing is, first we have to consider the wave function of the particle. The wave function, we know it is given by psi. It tells about the probability of finding a particle. So in a 3D structure, when we are talking about a density of state, we have to understand that the particle cannot reside outside the box. It should be inside the box, and it should not be on the walls. So what is the condition for the wave function? That wave function should be zero, means particle should not be there where we are saying first outside the box. The particle should not be outside the box, and secondly, it should not be on the walls, not on walls, not on walls. So these are the two conditions first that should be followed for a 3D structure, so that the particle which is inside the box, in which we are going to find out the density of state of in this three-dimensional structure, the particle cannot go outside, it cannot reside on the walls, it can only be within the box. So since we are talking about a wave function tells us about what? It tells us about the wave nature of particle. It tells us about wave nature of particle. It means if I am saying that particle cannot reside on this wall, it cannot reside on this wall, it means the wave of the particle can only travel between these two faces. Okay, the value should go to 0 here, and the value should go to 0 here on the faces, because it cannot reside on the walls. But the wave can travel between these 2 points, similarly between front and the left faces and top and the bottom faces. Okay, so the situation is like this, like as if I have taken a rope and I have clamped in between two ends, and the rope can only wave between these two. It means that the wave of the rope can travel between these two clamped points. These two clamped points are what? This is the this face and this is the this face. So electron wave can travel how? It can take like this, it can go and it can come back like this. It can travel like this, go and then come back like this. So anyway, it can travel between these 2 points. And such wave which are formed between two clamped points, we call that as the standing waves. We call them the standing waves. Okay, so we get standing waves formed between these inside this cuboid. Now the next thing. Now suppose what I am explaining next is that we will be talking about the phase of the wave. Now that the wave that is traveling. So since wave function, the wave is oscillating, okay, periodic it is. So for periodic wave, we write the wave function as this, iota kr. We are using r because we are talking about the three dimension. If we are talking about only single dimension, we like it for x direction, we can put it x. But since we are talking about three dimension, so the wave function is given by psi equals to uk e to the power iota kr, where uk is the periodicity and e to the power iota kr is the equation of a plane wave. Okay. Now what does this k dot r? This k is actually a vector, this r actually is a vector. What does this represent? This represent the phase of the wave. This represent phase of wave. Okay, phase of wave, because you can simply compare this e to the power iota kr to e to the power iota theta. So this theta is k dot r. Okay, this theta is what? This is k dot r, and this k dot r is what? This is a propagation vector, dot product with a position vector. This tells about the phase of the wave. So now we will consider this phase of the wave. Now for a round trip I am talking about, for a round trip. For a round trip. What do you mean by the round trip? Round trip means that the electron starts from this phase. This phase goes to this phase, okay, one trip, and then again coming back to its position. So this will be a round trip. That is, it is starting from this phase, going to that phase, and again coming to its phase. So this will be a round trip. So for a round trip, the phase will be what? When going from this point to this point, it will be k dot r, and then again coming back, it will be k dot r. So we have twice of k dot r. Twice of this phase should be equal to what? It should be equal to integral multiple of 2 pi, where n represents an integer, and this why integral multiple of 2 pi? Because when the rope was fixed between the 2 points, the angle it was making was pi. So while coming to this end, pi angle, and again coming to this end, pi angle, so it will be pi plus pi, 2 pi. So this is the relation for a standing wave we are getting, that twice of k dot r equals to n times of, that is integer of integral multiple of 2 pi. Now we can simply cancel out the 2 from here and we get this term. Now I am putting the value of this k vector. The value of k vector will be what? I cap kx plus j cap ky plus k cap kz. This is the k vector dot product. Then we have I cap x plus j cap y plus k cap z. This is a position vector and equals to what? N pi. We have this thing. This is simple a dot product. You can do the dot product. What we get? We get xkx plus yky plus zkz equals to n pi. Okay. Now what is this all thing? See, this kx, ky and kz, these are what? These are the individual axes in the k space. When you are talking about the momentum space, then kx, ky and kz represents what? It tells about the three coordinates, that is x, y and z direction in the momentum space. And these all kx, ky and kz are perpendicular to each other. So we can call them as the orthogonal components. Okay, we can call them as orthogonal components. And in orthogonal components, each one of these will be equal to n pi. Means this xkx will be equal to n pi, yky will be equal to n pi, means each one of these will be equal to n pi. So next we will be doing that only. So what we will be doing? The next step, I am equating each one of these. Xkx equals to n pi, yky equals to n pi, and zkz equals to n pi. Now one thing we have to see here, that these all are equals to n pi, that I have understood because they are the orthogonal components. But this n, what is this n? N is an integer. And if I keep the same n in the three equation, it means all of the three should have the same value. But since these kx, ky and kz are the individual axes, it is not necessary that all the integers can be the same. It may be same, but it is not necessary that it should be same. So instead of writing a capital M, n, I am writing M, P, Q. And what are these M, P, Q? M, P, Q are integers. Why I have replaced it? Because this capital N, if I put, it shows like that all the three integers should be same, but it is not necessary. So we have used now MPQ. MPQ are what? These are all the integers, but they can be same, they can be different. Okay. So now let us understand how can they be different. Let us take one example. Suppose like these are the three axes, and suppose I am again having a cube. Or let us see, let the point is here somewhere. It's not necessary to make a cube. So let us see that there is a point here, and this is x, this is y, and this is z. And that let the dimension, this is 1, this is also 1. So what does it tell? See, this one has a height also, because in terms of axis also it is having 1. So the coordinate will be 1, 1, 1. In this case means M, P, Q all have the value 1. This is M, this is P, this is Q. But if the point is somewhere here, then what is the value of this? The value will be that it is lying in the xy plane. It means the value is 1, 1 1 0, because it is having x, it is having y, but it is not having z, because it is not having the height. So in this case we can write, see that this is m, p, q. So in this case the three are not equal, they are different. So this is what I am saying, that it is not necessary that they all should be equal, they can be different also. Okay, like somewhere, if I take a point here, if I take a point here, then what will it be? It will be only 1, because the point is lying on the x-axis, so x will be 1, and y and z will be 0, because the point is lying on the x-axis. So this mpq all are different now. So that's the point that I'm going to I was explaining you. That's why I cannot put the same constant for the integer. It is not necessary that they all will have the same value. They can have the different value, they can have the same value. Okay, so I think this is understood to you. Now next thing, so from this equation, now what we get from this equation, I'm going to find out the value of kx. Kx will be what? M pi by x. Similarly, I'm going to find out ky. Ky will be p pi by y, and this kz will be your q pi by z. So this is what we are getting. Okay, so we got the value of kx, ky, and kz, and now what does these values mean? What do we understand by these values? Let us see that. So that I have the three dimensions in the k space. This is again your, this is your, suppose now your ky, kx, kz. Now I am talking about the k space, and this is our origin. Okay, kx, ky, and kz axis we have. Now let us plot anything like kx. I am plotting. So for kx, what we have kx? We have kx as m pi by x. So for the first point will be what? If I take the first point on kx, for first point I have to put m equals to 1. And for m equals to 1, what value I will get? I will get pi by x. So let this be the first point, and I am getting value pi by x. For the second point, I have to put 2. For second point, I will have to put 2, and the value I will be getting will be 2 pi by x, because instead of m I will be putting 2. So let this is the second point, 2 pi by x. Simply I'll get the 3 points, third point as 3 pi by x, fourth point as 4 pi by x, and so on I will get. But now what we see, the distance between two consecutive points is what? You can check in any of these, the distance between two consecutive points is pi by x. Whether you see between 2 pi by x and pi by x, the difference is pi by x. Whether you see between 4 pi x and 3 pi by x, the difference is pi by x. So the smallest distance between two points is pi by x. Okay. And similarly on the y and z axis, it will be like on the y axis, the difference between 2 points will be pi by y. And on the z-axis, the difference between 2 points will be pi by z. So this is what we mean by this m1, m2, the value of this integer. The different every value correspond to the next point. M equals 2 means 1 means first point on kx, 2 means second point of kx. Point means what here? Point means the allowed state. Means first allowed state, second allowed state, third allowed state, fourth allowed state, and so on. So this tells us about the how many allowed states are there in a particular direction we are talking about. Okay, so I think this is clear to everyone now. So the next thing now what we will be studying is what will be the minimum value of k and what will be the maximum value of k. Now we will be understanding that thing. Minimum value of k and maximum value of k. So minimum value, we have minimum value. We are talking about suppose x direction. So kx minimum is what? We put the value m pi by x, and we for minimum value I will put m equals to 1. So I get that pi by x is the minimum value of in the kx direction. Okay, for m equals to, because m equals to 0 we understand that will be origin only. So m equals to 1 is the minimum value in x direction. So now let us, for better understanding, now I am considering a cube. Okay, to understand this thing better, that what is the minimum value, what is the maximum value, and how many points are there on a certain axis, how many allowed states can be there. So let us again, I am considering a cube, and from that cube we'll be understanding the things. Okay, so This is your ky, kx, kz, and we have a cube. And let us consider that each dimension of the cube is of 1 mm. Means this is 1 mm. What is this? This is ky. Means your, or we can say it ly, length. Ly is 1 mm. It is 1 mm. This is what? This is lx. Lx. This is also 1 mm, and this is what? This is the height, Lz. Lz is also 1 mm. So Lx, Ly, Lz all are of 1 mm. We have taken a cube that has a dimension 1 mm. Now, so instead of now putting the value pi by x, now I can put at pi by lx, because now we have specified the values of in x direction. We have taken a cube and the x dimension is now lx. So putting the value 1 mm, what I am getting? I am getting 10 to the power minus 3 meter, and so I will get 10 to the power 3 pi meter inverse. Okay, so this is the minimum value I'm getting for the k. In a kx direction, the minimum value can be this pi by lx, and in the, if we understanding by quantitatively, it will be this. Now, what is the maximum value it can have? What is kx max? So the maximum value in the kx direction can be obtained by using the formula. Formula was what? 2 pi by lambda. Lambda here is what? It is the de Broglie wavelength of the electron. De Broglie wavelength of the electron. So this lambda, for this kx to be maximum, lambda should be minimum. For kx to be maximum, lambda should be minimum. Then only we will be getting the maximum value of kx. So for a lambda to be minimum, let us consider that this is your Lx. We are considering one dimension because we are talking about the x direction only. So let this is your x direction. These are the atoms sitting in that x direction. Okay, and these are the atoms sitting, and let the dimension we have already mentioned that it is Lx. Dimension of the cube is Lx. Now we have to find the lambda minimum. For lambda minimum, suppose we consider that the electron is coming from this side. So when the electron comes from this side, it saws the electron nuclei is there. So nuclei attracts the electrons towards itself. That's why the electron starts to bend towards the nuclei. But when it comes closer to the nuclei, what happens? There is repulsion from the electron cloud. So what happens? It will scatter away. Then now it will travel. Now again it saws a nuclei here. It goes towards it, but again it is scattered from the electron cloud. So this is how we will be getting an electron wave that is nearest to the nuclei. Okay, this is the wave with the smallest wavelength. So in this case, if we find out the wavelength, what is the wavelength? Wavelength is the distance between the two crusts. So if the interatomic distance is a, interatomic distance is a, then we can see that the wavelength we are getting from here to here is 2a, because this is a and this is a is 2a. So for the smallest wavelength, lambda minimum, we are getting as 2a. Putting this value, what we get? Now we can find out that the k maximum, kx maximum equals to what? 2 pi by 2a, and this cancels out, we get pi by a. This is the maximum value we can get in the kx direction. Now suppose we define this a value also. Let the interatomic distance. Let this interatomic distance is 5 angstrom. If the interatomic distance is 5 angstrom, we can write that pi by 5 into 10 to the power minus 10 meter, and solving it we can get 2 into 10 to the power 9 pi meter inverse. Pi meter inverse. This is what we'll be getting. Okay, so we see that the minimum value we were getting was 10 to the power 3 pi meter inverse, and the maximum value we are getting is of the order 10 to the power 9 pi meter inverse. So in going from minimum, k minimum to k maximum, there is a change in 10 to the power 6 orders of magnitude. Okay, it varies to 6 order of magnitude when we go from kx minimum to kx maximum. Now what does it tell? It tells that suppose this is your k space. You are very familiar with this ek diagram. This is k, this is e. So what we are saying, this is the minimum value. Okay, this is the minimum value. At this minimum value, there were 10 to the power 3 states were there. Okay, but when we go from this to the top of the band, that is at the pi by a, pi by a is the top of the band, the number of states increases to millions, 10 to the power 3 to 10 to the power 9. Okay, so we can say that there are millions of states on a particular axis that rise in the range of 10 to, that increases from 10 to the power 3 to 10 to the power 9. Okay, so in a particular axis there are millions of states, millions of allowed states are there in a particular direction. Similarly, in y and z direction there are millions of allowed states that we are getting. The k values, the maximum k value we are getting in the order of 10 to the power 9. Okay, and the minimum we are getting to 10 to the power 3. So there are millions of values, millions of allowed state on a particular axis. So million of kx are permitted. Similarly, we can say there are millions of values on ky and kz also are present. So we can say that in all the three kx, ky and kz direction, each one can take a million value. Okay. So now the next thing we are going to understand about now we will be calculating the density of states. These things were important to understand what we are going to find out further. So for the density of state in 3D now, first what we are going to find out, the volume occupied by the smallest state. Now the volume occupied by smallest state. Smallest state means that we are talking about a smallest cube, because we are talking about a three-dimensional structure. So what will be the volume occupied? The volume occupied will be pi by Lx, because this was the smallest value k can have. In x direction, pi by Ly, this is the smallest value in the y direction, pi by Lz. So length into breadth into height, this is the volume of cube. So this is the smallest volume that can be occupied by a state or a cube. Okay. Now the next thing, what is the total volume available to the electrons? Total volume available to the electrons between a k and k plus dk. For that, we know that when we are talking about a three-dimensional structure, only the octant is allowed. Only in octant the electron can attain the values, can get the values, because the other parts are that are taken as a forbidden states. Okay, so we consider only the positive half, or we consider only the octant of a sphere. Therefore, let us draw that octant first. Let us draw that octant like this. So this is that octant that is available. Okay, and let this value here is k. Now let this take another value at the back side of this sphere, means at some distance from this, and let this value is d plus k plus dk. This value is k plus dk. So the width of this section is what? The width is dk. Now I have to find out what are the number of states that are available in this dk interval, or what are the volume, what is the volume accessible in k and k plus dk. This is the octant we are considering actually. Okay, in a sphere only the octant is allowed. So we can write the volume between k and k plus dk is V equals to what? It will be 1/8 of the surface area, first surface area. Surface area of the sphere is 4 pi r square. In this case, we have 4 pi k square, because we are considering the momentum space. Okay. So 1/8 of this surface area. Why we have taken the surface area? Because this is the front surface that we are facing it. Now multiplied by the width. Width is what? Width is dk. So this is the volume that is available between the k and k plus dk. This is this volume we are talking about. Okay, this is the shaded portion we are talking about. So in this volume, this is the total volume that is available, and the volume occupied by one is stated this. Now we can find out how many number of points are there. How we can find out that? Number of points will be what? Total volume divided by the volume occupied by one state. Okay, that's how we will be calculating it. So in the next lecture we'll be going further. So the next lecture will continue and we'll be finding out the number of points lying between k and k plus dk. Okay, thank you.